first strategy consists to prove using standard techniques that x times x minus 1 is equal to 0 modulo some q prime, where q prime is a prime number close to A. It can be, for example, the next prime of A. And we show that showing this, this constraint is sufficient to prove that X is binary. The second strategy works as follows. We will get a sharing of a random mask R, which is ensured to be binary thanks to a cut and choose phase. Then we compute and reveal the mask version of the secret X, named X tilde, as X XOR R. Then we can deduce a sharing of X using the above relation. Since we know that X tilde is binary and that R represents a binary vector, thanks to the cut and choose phase, we directly have that X is a binary vector. Using the previous strategy or this strategy, we can build our MPC protocol. Then we can apply the NPC paradigm to get a zero knowledge proof of knowledge for the subset sum problem. When in a standard case, use case, the verifier accepts the proof as soon as the prover does not abort during the two repetition of the protocol. In our case, we will relax this statement. Instead, the verifier will validate the proof as soon as the prover does not abort more than eta times, where eta is a parameter, a new parameter. It increases a bit the soundness error, but it will decrease a lot the rejection rate, and it will provide better trade-offs than simply increase the upper bound A of the sharing scheme. Here are the performances obtained when building proof of knowledge for the subset sum problem. We can achieve communication cost below 20 kilobytes, while the former schemes have communication costs larger than 100 kilobytes. We applied our sharing technique to the subset sum case, but in our work, we show that we can apply this sharing technique to other applications. In our work, we propose 3 other applications. The first one is to build zero knowledge proof of knowledge for the short integer solution problem. Given a matrix A and a vector U, the short integer solution problem consists to find a vector S such that we have this linear relation and such that the infinity norm of S is less than some bound beta. Then, using exactly the same technique as before, we can build zero knowledge proof of knowledge for this problem. The obtained performances is the following one. We can observe that we get efficient alternative in the case where the ring is not small or entity friendly. More precisely, we can remark that the proof size is independent of the ring size. And so if we increase the ring size, the proof size would be the same and we will be more competitive compared, for example, with the former schemes. The second application is for the TF-8G context. In our work, we build a protocol to prove the knowledge of key plain text pairs matching to a given ciphertext. And we gain a factor between 10 and 20 compared to, for example, the Shamir's protocol when we applied the Shamir protocol to this use case. As last application, we propose to build an efficient signature scheme from Bonnet, Halevi, Graham PRF. This PRF, using a secret key X and a message M, output the most significant bit of the inverse modulo P of X plus M. The private key of our signature would be the secret key of the PRF, and the public key of our signature would be some outputs of this PRF for public constant 1, 2 until T. And the signature will be a non-interactive proof of knowledge of the secret X and the less significant bit of the inverse in the PRF. And so the proof proves that if we concatenate the small less significant bit with the most significant bit, we get the inverse of X plus the message. And we need to prove that X, Z1, Z2 is small. And to prove that, we use our sharing scheme. And since for example, Z1 will be shared into a sum of small value, we will directly have that Z1 is small, but with some slack. And we will select our signature parameters so that it is secure with the slack against the known attacks against the PRF. The resulting signature size of our scheme is around 5 kilobytes, which is competitive with the current state-of-the-art of the MPC-in-the-head based signature like Rainier. To conclude, in this work, we propose a new sharing technique to share small value when using large modulus. To avoid information leakage, we add a rejection rule. And then we can, using this technique, we can build efficient zero-knowledge proof of knowledge for the case of the subset sum problem. And there is other application like in FHE of to build efficient signature. As perspective, we can try to find other application of this sharing technique. And our signature scheme could be a good candidate for a post-quantum scheme, but it would be nice to have a quantum cryptanalysis for the Bonnet and Hals PRF. Thank you for your attention.
Okay, thanks for the talk. Are there any questions? Okay, so maybe I'll start with one quick question. So you motivated this subset sum problem, and you mentioned briefly that you're interested in the big modulus, for example, 2 to the 256. Is there any particular reason why we consider such big moduli?
It's because the cost of the sharing well, the cost of the sharing offset will scale with the size of the modulus. And since we are now independent to the modulus Q, we will be more efficient with a very large Q compared to if Q is small. In practice, we take A around 2 to 15. 2 to 15, yes. So it costs per bits, per coordinate, it could cost 15 bits. But in case of the subset sum, the previous technique used more than 200 bits. So there is a very big communication saving. It's less impressive when we use small modulus.
Okay, and could you please show the slide with comparison with other schemes like the lattices and Aurora Ligero, please.
This one?
Yeah. So you mean that in your protocol, you can pick, so the sizes would, so could you repeat this, your remark about picking, oh, so you said that if you pick bigger moduli, then the proof size stays the same. It's not.
Yes,
dependent.
yes, it's independent of the ring size. So if we take a very large, we will beat the other schemes. In the case of 2 to 30, we are equivalent to Belen's works, but on larger field, we will outperform the other scheme. Since we are independent of the ring size.
And just out of curiosity, if we just take Q to be 2 to the 15, then what will happen? Or like even smaller?
15.
Yeah.
But in fact, our proof will be quite the same. So it
okay.
will be very uncompetitive compared to the state of the art. Because we will have around 200 kilobytes, even for the small Q. So yes, the ID is very competitive only on large field.
Okay, thanks. Are there any other questions? Okay, then let's thank the speaker again. So we have the next talk, which is about efficient zero-knowledge arguments in discrete logarithm setting, sublogarithmic proof or sublinear verifier. It's work by Sung-Wook Kim, Hyun-Bom Lee, and Jae-Hong So. And Hyun-Bom will give a talk.
Hi everyone, I am Hyun-Bom Lee, and I'm going to talk about our paper, efficient zero-knowledge argument in discrete logarithm setting, sublogarithmic proof, or sublinear verifier. This work is joint with Sung-Wook Kim in Solomon University and Jae-Hong So in Hanyang University. I'm explaining zero-knowledge argument of knowledge briefly. The zero-knowledge argument of knowledge is a proof system between the prober and the verifier. The prober claims the knowledge of a witness, which is satisfying some relation given instance X. So zero-knowledge argument of knowledge should satisfy 3 properties: completeness, knowledge soundness, and zero-knowledge. If the instance and witness is belong to the relation, the prober can convince the verifier. And without knowledge of the witness, the cheating prober cannot convince the verifier. And zero knowledge, the profile reveals no information except prober's knowledge of witness, which is belong to the relation. And we call an argument is transparent if the argument does not require trusted third party for generating common reference string, CRS. And now, before introduce our contribution, I'll briefly explain inner product argument, IPA. So the inner product argument is an argument of knowledge of 2 vectors for their inner product relation. The transparent inner product argument with logarithm communication is introduced in Elliptic 16, and optimized version is introduced in SNP 18, which is known as bullet proofs, and I will call these bullet proofs to BPIP. And inner product argument to IPA is used in some application, zero knowledge range proof, zero knowledge argument of arithmetic circuits, and zero knowledge polynomial Kahneman scheme. There is a reduction from zero knowledge argument for arithmetic to inner product argument to IPA. So we focus on BPIP and its variant for constructing GKA, zero knowledge argument. And this is our contribution. We propose 3 transparent IPAs. First, protocol 2, the first IPA with sublogarithm communication. Second, protocol 3, the first IPA with sublinear verifier under discrete log assumption. Last, protocol 4, introduce a novel method to achieve the sublinear verifier IPA without pairing. And this is the diagram for our contribution. First, we observe the BPIP as two-way communication and verification. After the first generalization, we construct protocol 1 using commit and proof approach. But the protocol 1 is not as efficient as we wish it. So additionally, we apply aggregation technique, and finally we get protocol 2. And another generalization, we construct protocol 3 by substitution CRS and we propose new 2-tier commitment without pairing, and we adapt this commitment to protocol 3, and finally we get the protocol 4. Now I'll explain protocol 2, sublogarithmic communication. The blue one is the keyword for the constructing protocol 2. This is the observation for communication of BPIP. The key idea of logarithmic communication is witness reduction. The half witness vectors A and B and update to A hat B hat recursively, and A hat B hat are updated by the following the formula. The prober should send commitments to cross terms. I notify this formula cross terms per round. So total communication of BPIP is total rounds times each reduction cost, and which is 2 log n. Then how about reducing witness vectors more shortly? We construct generalized BPIP from 2n partition technique. Then we expect to decrease total rounds to log n based 2n, but each reduction cost may increase. And let's look at the more detail. The parse witness vector A and B to 2n subvectors and update to A hat B hat recursively. And A hat B hat are updated following the relation. Then the prober should send commitments to cross term, which are 2n-1 group elements per round. For constructing commitments to cross term, the prober comes O small n large n group exponentiation. And total communication is round times each reduction cost. And the total communication is this, and n is 1 is optimal value of total communication. So there is no merit to use 2n partition technique. To reduce communication cost, we apply commit and proof approach. The prober sends a short commitment rather than sending 2n-1 group element V. But without V, the verifier cannot update to next instance P hat. Then how to construct a reduction protocol? The solution is that the prober send updated instance p hat with prof pi after receiving challenge. The prof pi is proof of knowledge v such that p hat is v to x, which x is public from the challenges. The from construct prof pi, we construct a multi-exponential argument, MEA, and MEA can construct similar way to IPA. Next. Then after applying common and probe approach, then for each round, the probers and Coinman and update instance p hat and probe pi, whose size is O log small n. Then total communication of protocol 1 is O log large n. In terms of communication cost, protocol 1 is the same as VPIP. To reduce communication more, we apply aggregation technique. The aggregation technique is this, generating one aggregated probe for multiple relations. This is a diagram for protocol 1 and 2. In protocol 1, after the commit and probe approach, the proper send commit mount and updated instance p hat and pi for each round. After the aggregation technique, the prober send commit mount and p hat for each round, and the last round, the prober send aggregate probe. And the complexity is this. And let's focus on communication cost. So round reduction, in round reduction, the communication cost is O log large n based to n, and aggregation probe, this probe communication cost is O log large n based to n plus log small n. Then total communication cost is this, and let's small n is 2 to the square root log n. Then we get O square root log n communication. But the total prober complexity is increased to O large n times 2 to the square root log n. This is a kind of trade-off to prober complexity and communication cost. Next, protocol 3, sublinear verifier under the discrete law. This is the observation of BPIP respect to verifier. In BPIP, sample G and H uniformly and use them as common reference tree. For each round, the prober and verifier have group elements G and H and update to G hat, H hat following the formula. This update requires 2n group exponential, which is linear. To avoid linear verification, we consider to change CRS form. To change CRS form, I introduce new notion, outer pairing product. Let's G1, G2, GTB group of prime order P with bilinear map E. And let's define the outer pairing product for group element G and large H. Define G type H is this. This is a kind of canonical product. And let large N is M times N, be a vector length of our IPA. Then how about using G times H, H times large H, rather than GH, which is N group elements on BPIP. BPIP provide knowledge soundness under discrete logarithm relation assumption, and it is known as DLR assumption is equivalent to DLR assumption. DLR assumption is this. It is interactive to find a non-trivial relation such that G to the G is identity. So we construct a new theorem. We state and prove this theorem for adapt. The to prove soundness of our protocol. The theorem guarantees hardness of finding non-trivial relation of G times H, which is guaranteed the soundness of our protocol. Then, and we use small g and h and large h as CRS of our protocol argument IPA protocol 3. And this is a kind of visualization of protocol 3. First, start the row reduction. So witness matrix is half row matrices, and prober and verifier half the G1 part in CRS and keeping G2 part. And after the row reduction, the program verifier run column reduction and keeping the G1 part, just half to G2 part. Then the complexities focus on the verification. In row reduction, the verification is OM, and in column reduction, the verification cost is ON. So the total verification cost is OM n plus n, and let's m equal n equal square root to n, then we get O square root to n verification, which is sublinear. Next, I'll explain protocol for sublinear verifier without pairing. This is another view of protocol 3. In protocol 3, we construct G times H for complement to matrix A. The another view is two-tier complement. Two-tier complement is complement via two steps. First, for all J column vectors of matrix A and commit to column vectors AJ using patterns complement. After the complement, first step, commit the results of first complement using AFGHO complement, which use pairing. To complement the result without pairing, we consider a complement to elliptic curve point. There are two elliptic curve representation, affine representation on GQ square and projective representation on GQ cubic. It is hard to represent point at infinity from affine representation but there is a complete addition formula from projective representation. So we consider the projective representation for elliptic curve. From projective representation, we consider elliptic curve as a vector in GQ cubic and then apply Pellet's complement to the vector. Next, I introduce our new two-tier complement. First, set a pair of elliptic curve, GP and GQ, which is elliptic curve of order P and Q, and the GP is elliptic curve over GQ. And after first complement, consider the result group elements as vectors over GQ, and apply second complement, pattern complement based on GQ. And the complement guarantees binding of message, but not provides homomorphic property. Without homomorphic property, the verifier cannot update P hat, which is similarly in protocol 1. So we apply commit and probe approach similarly in protocol 1. Then for each round, the prober sends updated instance P hat with probe pi to the verifier. After using commit and probe approach, total probe size is O log square n. To reduce total probe size more, we apply aggregation technique like protocol 2. Then what should the probe pi convince? The probe pi is to convince that knowledge of elliptic curve point satisfy elliptic curve relation. The instance is element of Q, and the witness is element of GP, and the large one is the coimage of small letters. And the process is this: represent elliptic curve relations using complete addition formula and use argument of knowledge for arithmetic circuit on GQ or converted from complete addition formula. Then the proof size is O log small n and verification is ON. So from this way, we construct two arguments, multi-elliptic curve argument for row reduction and column reduction. This is a visualization for protocol 4. First, commit proof approach. The probers and L are P hat and the probe for each round, but we apply aggregation technique more. And actually the probers and the L are P hat and last round, the probers and the aggregate probe. And this is the complexity. The total communication is O log Mn, and the total verification is O m plus n log m. Let m equal n equal square root n, then we get O square root n log n verification. So this is conclusion. We propose 3 transparent IPAs, which can be combined to reduction GKA to IPA. From the reduction, we construct 3 zero-knowledge arguments. First, zero-knowledge argument with sub-logarithmic communication. As far as we know, this is the first sub-logarithmic GKA in transparent setting. Second, GKA with sublinear verifier under DL assumption. Although the argument uses pairing operation, its soundness is based on discrete logarithm assumption. Actually, there are another sublinear verifier GKA under DL assumption and more assumption, but we proved that DL assumption is enough to the sublinear verifier GKA. And last, GKA with sublinear verifier with pairing. Without reliance of pairings, we show possibility of sublinear verifier in the DL discrete log setting. Thank you for attention on my presentation.
Yeah, thank you for your talk. Are there any questions? Okay, let me start with one. So could you please comment on the comparison of the knowledge soundness error of protocols 2, 3, and 4 with bulletproofs?
Yeah. The comparison, in my memory, I did this content is in our paper. So briefly say actually the soundness loss is occur to protocol 3 and 4 about 1/q maybe. And so more detail, please check our different paper.
So just to make sure, is it going to be the same as for bulletproofs, or is it slightly larger? Obviously, I guess negligibly larger, but
larger, but also negligible.
okay. Are there any more questions? Okay, so let's thank the speaker again.
Thank you.
Okay, so the last talk is online. Non-interactive zero-knowledge proofs to multiple verifiers. And this is a paper by Kang Yang and Xiao Wang. And Kang will give a talk.
Okay. Do you see my screen?
Yes.
Okay. Hello, everyone. I'm Kang Yang from State Laboratory of Cryptology. This is the joint work with Xiao Wang from Northwestern University. Our work is entitled Non-Interactive Zero-Logic Proof to Multiple Verifiers. Zero-logic proofs enable a prover to convince a verifier a statement is true. Here, statement X is often represented by a circuit. W is called weightless. In this case, XW satisfies an NP relationship is equivalent to CW is equal to 0. ZK proofs lead to satisfy three properties. The first is completeness, means when the prover honestly executes the protocol, the verifier must accept. The second is soundless, means the malicious prover cannot convince the honest verifier a false statement is true. The third is zero knowledge, means the malicious verifier cannot learn any information except the statement is true. NIMVZK allows the communication between a prover and a verifier to be non-interactive. NIMVZK is publicly verifiable, and a proof can be reused to convince multiple verifiers. And the efficiency of NIMVZK has been significantly improved under different frameworks, such as MPC in the head, GKR, IOP, and so on. Designated verified ZK, that is DVZK, is often an interactive protocol between a prover and a verifier. DVZK can convince only one verifier every time. DVZK can be constructed under different works, such as Gabor circuits, VOE, COT, and so on. In general, NIMVZK has a sublinear verifier time. Sublinear proof size is non-interactive and supports any number of verifiers. Compared to NIMVZK, DVZK has faster proof time, faster total time, small memory. Therefore, NIMVZK and DVZK have different efficiency features. We come to explore the middle ground between NIMVZK and DVZK. Particularly, we study the efficiency of ZK proofs when the prover wants to convince multiple verifiers, that is NVZK. We allow the adversary to corrupt up to T of the N verifiers, and let the corrupted verifiers can collude with the prover. We focus on the case of T less than N over 2. Our goal is to design concretely efficient NVZK proofs, achieving significantly less communication than running NDVZKs, having runs close to NIMVZK. Support streaming these proofs that obtains more memory. Here, streaming a proof means the prover can generate and send the proof on the fly, and the low party needs to store the whole proof during the protocol execution. In the NIMVZK setting, there are two types of communications. One is between the prover and the verifiers. The other is among different verifiers. If the prover only sends one message to every verifier, then the protocol is a non-interactive NIMVZK, that is NIMVZK. If there is only one round of communication between verifiers, then NIMVZK is called strong NIMVZK proof. We allow the verifiers to communicate for one round because without any communication between verifiers, constructing NIMVZKs appears as difficult as constructing NIMVZKs. Here I list some potential application of NIMVZK. NIMVZK can be used as a drop-in replacement to NIMVZK and DVZK, as long as the identifiers of verifiers are known ahead of time. Our NIMVZK proofs can be used to design honest majority MPC with the input predict check to achieve better efficiency. NIMVZK can also be used in private aggregation systems when allowing users to collude with a minority of servers. We proposed three new concrete efficient NIMVZK proofs with streamable property. The first protocol is information theoretic. The other two protocols are computational security. The two protocols in the state setting are our main protocols. All our protocols need only one round between the prover and the verifiers. The protocols in the state setting need also one round between verifiers. There are two protocols in the setting protocols. All our protocols are streamable and have small memory. For computational complexity, our protocol, For computational complexity, our protocols are linear to the circuit side, are cheaper than NIMVZK. When streaming a proof, our strong NIMVZK protocols keep one round of communication among verifiers. Our strong NIMVZK proofs also have uninteresting asymmetric characteristic. That is, T verifiers have sublinear communication and can be lower resource mobile devices. Previous strong NIMVZK protocols, ACF02, G007, require public key operations and are not concretely efficient. Prior works BBCGI lighting BGIN20 on distributed ZK implies NIMVZK proofs on low degree polynomial or degree 2 relation instead of generic proofs. Prior CB17 does not allow the prover to include any verifier and requires quasi-linear instead of linear computation. Compared our NIMVZK protocols with concurrent works, our protocols has a higher efficiency but a lower security. In particularly, while AKP22 achieves the full security and BJOSS22 obtains identifiable abort, our protocols get a security with abort. Here, full security guarantees all verifiers must obtain an output. Identifiable abort allows honest verifiers to identify one of the cheating parties. Now outline our framework for building NIMVZK protocols. Will adopt linear secret sharing schemes such as Shamir or packet secret sharing. Accurately replicated secret sharing also work for our framework. For secret X, we use square bracket of X to denote a sharing of X and use Xi to denote the shares sent to verifier I. For each input wire and output wire of multiplication gates, the prover shares the secret values to every verifier. Then we use the distributed ZK, that is DZK technique, to check correctness of series of multiplication gates. To achieve strongly non-interactive, we propose the distributing Shamir technique. In particular, the prover broadcasts COM1 to COM-N to every file. Here COM-I is the commitment of shares held by verifier I. Because we work in the answer majority setting, these commitments determine all secret wire values. Therefore, we have public messages to make Shamir work. We give an OM output describing the main idea behind the information theoretical NIMVZK. First, the prover evaluates the circuit by sharing output of each gate. Due to the linear property of secret sharings, addition gates can be locally evaluated by verifiers and are free. Then prover and verifiers transform the checking multiplication gates into the checking of an inner product tuple. Particularly, the verifiers run a coin tossing protocol to generate a random challenge, then compute series of vectors x, y, z like this. Here, sharing of z is computed as the sum of xi multiplied the sharing of zi. Next, the verifiers use DZK to check correctness of the tuple xyz. In the procedure, the prover generates random sharings to mask sharings of secrets. Due to usage of coin tossing, we need to run logarithmic to circuit size. Strong NIMVZK from Xiaomi series has the same framework as the information static NIMVZK. The challenge is to compute a public message can be used as the input of RO. However, only secret shares are sent by the prover to every verifier. Therefore, the verifiers have no way to compute a public message. Suppose prover sends MI/RI to verify I. Here, MI consists of secret shares. To solve the challenge, we let prover compute COM_R equal to HMI/RI and send COM_1 to COM_N to every verifier. Here, H is the commitment, is the random. Verifier I checks correctness of COM_I. Because T less than N/2, majority of commitments are correct. Finally, the verifiers compute the challenges equal to H prime COM_1 to COM_N. According to our analysis, H prime are unnecessary to be Collision resistant, and it's sufficient to guarantee random output. So we can adopt lambda rather 2 lambda as the output length. More importantly, the construction DNNR17 based on phase key AES can be used. The communication overhead is N2 lambda bits is small. The first two NIMVZK protocols adopt Xiaomi series. A T-degree polynomial F is computed such as F0 is theta as secret S, and F of I is the share of verifier I. We can generalize the Xiaomi series into packet series to setting K secrets in K different positions. That is, we can set F beta I equal to secret Si. The downside is lower corruption threshold. We often use the square bracket of vector X to denote a packet series. When using packet series in strong NIMVZK protocol, we can perform addition or multiplication operation for a group of K gates every time. If the packet sharing does not exist, prover needs to generate and distribute Y for every group. There exists some wires are in different groups, thus we need to prove consistency of wire values in different groups. Particularly, prover needs to prove correctness of wire tuples. A wire tuple is XY ij such as xi equal to yj. For each ij belongs to 1 to k, the verifiers need to check consistency M wire tuples with same indices ij. This can be done by random linear compilation. That is, x is equal to sum of alpha h multiply xh plus x0. Y is computed similarly. Then verifiers can open xy and y to check xi equal to yj. Here, x0 and y0 are random series such as x0i equal to y0j. So their lowology property is guaranteed. We use the fair Xiaomi to generate the challenge alpha equal to h prime uvij. Here uv the public messages to generate series of x0 and y0. As we allow a bot, we can use equal broadcast protocol. The hashing of messages is sent when opening series. Therefore, we can keep one round of communication between verifiers. To check correctness of packet multiplication tuples, the parties perform packet multiplication tuples into a packet inner product tuple. Now, the parties hold the series of x1 to xn, y1 to yn, and z. Here z equal to x sum of xi star yi, and the star is the component-wise product. Then the verifiers run a recursive reduction to reduce the dimension of a packet inner product tuple to 2. There is a log n minus 1 iterations without any interaction. Particularly for iterations, split a packet tuple into 2 packet tuples, then compress 2 tuples with dimension m into 1 tuple with dimension m over 2. Finally, the verifiers randomize the compressed inner product tuple with dimension 2. This randomization is done using a random tuple generated by prover. The parties compress the split tuples along the random tuple into 1 packet tuple. Then they open the resulting tuple to check z equal to x star y. The remaining task is to show how to realize the non-interactive compression of inner product tuples. Based on the polynomial approach in BBCGI Lighting GPS 21, we use the Fehr-Shamir to realize non-interactive compression. Specifically, we need to compress 2 packet inner product tuples into 1 tuple. For each j belongs to 1 to m, the parties compute a series of polynomial fj such that fji equal to aij, and compute a series of polynomial gj such that gji equal to bij. Then the parties also compute a series of polynomial h such that hi equal to ci. Then they compute a challenge alpha equal to h prime gamma and MSG. Here, gamma is the challenge used in the previous iteration, and MSG is the public message sent in the current iteration. The series xj, yj, z are defined as the series fj alpha, gj alpha, and h alpha. We can prove a large circuit batch by batch. Prover can prove n equal to k multiply m multiplication gates each time. For one batch, the parties non-interactively compressed a packet inner product tuple with dimension n into a packet tuple IP tuple 1 with dimension n divided 2c for some integer c. For another batch, the parties perform the same operations to obtain other packet tuple IP tuple 2 with dimension n over 2c. Then the parties non-interactive compress IP tuple 1 and IP tuple 2 into 1 tuple with dimension n over 2c. In this way, we only need 1 round between verifiers for all batches. The memory is open here. N is a parameter, can be set according to the memory size. A similar idea can be used for consistent check of wire tuples. Recently, Antman WYYXW22 first achieved sublinear communication for 2 parties ZK proofs in the VOE family. One open question is to construct an NIMVZK protocol with sublinear communication without requiring any computation-heavy tools such as FHE if it is not impossible. Our NIMVZK protocols work in the answer majority setting. Another open question is to design an NIMVZK protocol for t equal to n-1 has much better efficiency than running NDVZKs. Thanks for your attention. The full version can be found at ePrint. If you have any questions, then send emails to me. Thanks.
Okay, thanks for your talk. Are there any questions? So I just have a quick question. So you said that 2 protocols, the 2 new protocols they rely on, they have this computational security, right?
Yes.
This means that I guess, soundness relies on
here.
So that means that soundness relies on some computational assumption?
No, because We say they are in the computational security setting because we use random oracle. So the adversary must be polynomial time.
I see. Okay, thanks. Any other
Thanks.
questions? Okay, so let's thank the speaker again.
Thanks.
So that concludes the session, and enjoy the dinner.